Ever wondered how multiple data streams travel over the same network without interference? Welcome to the magic of multiplexing in computer networks, a technique that elegantly combines several data streams into one communication channel. This wizardry allows multiple users and applications to efficiently share the same physical medium. From the bustling exchanges of time division multiplexing to the harmonious separations of frequency division, the unique codes of code division, and the dynamic allocations of statistical multiplexing, each method has its role. Now let's dive into each type and see how they manage this digital wizardry. Imagine a train track shared by multiple trains, each given a specific time to pass. This is time division multiplexing. In the realm of computer networks, time division multiplexing, or TDM, is a method where the available bandwidth of a communication channel is divided into distinct time slots. Each slot is dedicated to a specific data stream, allowing multiple signals to share the same channel without interference. Here's how it works. Picture the day divided into 24 hours. Each hour represents a time slot allocated to a different activity. Similarly, in TDM, the transmission medium's time is sliced into sequential time slots. Each data stream is assigned its own exclusive slot during which it can transmit data. This sequence repeats cyclically so that each stream gets regular access to the channel. A classic example of TDM in action is the traditional telephone network. When you make a call, the network assigns a specific time slot for your voice signals to be sent over the network. This slot cycles back to you predictably, ensuring that your conversation flows smoothly without overlapping with others. The precision of TDM is one of its standout features. Since each data stream is confined to its slot and does not overlap with others, there is minimal chance of collision. This makes TDM highly effective in environments where predictable transmission is critical. However, TDM also has its limitations. The rigid structure of fixed time slots means that the bandwidth might not be used efficiently. If a data stream has nothing to transmit in its allocated slot, that portion of bandwidth goes unused. Moreover, as the number of devices or data streams increases, the individual time slots become shorter, potentially impacting the quality of data transmission. Despite these challenges, TDM remains a fundamental technique in many wired communication systems, especially where real-time data transmission is crucial, such as in audio and video conferencing systems. TDM's precise scheduling ensures no two trains, or data streams, crash into each other. Now, think of a highway with multiple lanes, each lane dedicated to one type of vehicle. Welcome to frequency division multiplexing. Imagine you're tuning into your favorite radio station while your friend listens to a different one in the same room. Both signals travel through the air over different frequencies without mixing up. This is frequency division multiplexing, or FDM, at play. It's a method that slices up the vast spectrum of frequencies available into distinct channels, so multiple transmissions can occur simultaneously without interference. In the world of telecommunications, FDM is a foundational technique. It divides the available bandwidth of a communication channel into multiple frequency bands. Each of these bands is like a distinct lane on our metaphorical highway. These lanes are assigned to different data streams, enabling multiple conversations or data transfers to occur at the same time on the same channel. Let's delve into a classic example. Traditional radio and television broadcasting have long relied on FDM. Each station broadcasts at a different frequency, ensuring that your favorite radio show and the evening news don't jumble together. This segregation allows you to switch between channels freely, choosing what you want to listen to or watch. However, like any technology, FDM comes with its own set of challenges. One of the main drawbacks is the requirement of guard bands. These are unused sections of the spectrum placed between channels to prevent overlap and interference. Unfortunately, this means that some of the available bandwidth goes to waste. Moreover, the system's efficiency can decrease in scenarios with a high number of channels due to this need for spacing. Despite these challenges, the benefits of FDM are significant. It allows for the simultaneous transmission of multiple signals over a single communication medium. This capability is crucial in scenarios where real-time data transmission is necessary, such as live broadcasts or emergency communication systems. FDM allows simultaneous data streams, each on their own frequency, cruising without interfering with each other. What if all cars on the highway could use all lanes at once, yet avoid collisions? Enter code division multiplexing. Imagine a bustling highway where every vehicle is allowed to use any lane at any time without the risk of crashing into one another. This is the essence of code division multiplexing, or CDM, a sophisticated form of multiplexing used in digital communication systems. Unlike other multiplexing methods that divide channels by time or frequency, CDM allows multiple data streams to coexist on the same frequency band simultaneously. Each data stream in CDM is assigned a unique code. These codes are not just random sets of bits, they are carefully constructed to ensure that each is distinct and orthogonal to the others. This orthogonality means that the codes do not interfere with each other despite sharing the same channel. Think of it as each conversation in a crowded room being spoken in a unique language. Everyone is talking at once, without waiting for their turn, yet you can understand the conversation you're engaged in because it's in a language only you and the speaker share. In the world of mobile communications, CDMA, or code division, multiple access utilizes this very principle. Each mobile device is assigned a unique code that modulates its transmitted signals. When these signals reach a cell tower, the system uses a correlator to decode each signal based on its unique code. This process effectively separates out each mobile user's data from the composite signal, ensuring clear and distinct communication channels. The decoding process at the receiver's end is equally fascinating. It involves a correlator that identifies and isolates the intended signal from a sea of overlapping signals, using the unique code to reconstruct the original data. This is akin to picking out a single voice in a chorus, recognizing it through its distinct pitch and tone. CDM's ability to allow multiple transmissions over the same frequency band without interference optimizes the use of available bandwidth. It's a brilliant solution that maximizes efficiency in crowded network environments, much like our metaphorical highway. CDM's unique coding system allows a dense and efficient use of the shared spectrum. Imagine a smart highway that dynamically allocates lanes based on the current traffic demand. That's statistical multiplexing. In the bustling world of data networks, statistical multiplexing acts much like this intelligent highway system. It doesn't just split bandwidth into static slots or frequencies. Instead, it dynamically adjusts the bandwidth allocated to each data stream based on real-time demand. This ensures that network resources are used efficiently and effectively. Let's delve into how this works. In a network using statistical multiplexing, multiple data streams from different sources, like video, audio, and text, share the same communication channel. Instead of pre-assigning fixed portions of bandwidth, the system continuously analyzes the network traffic and allocates bandwidth where it's needed most. It's akin to adding more lanes to our highway when traffic is heavy or narrowing it down during quieter times. This type of multiplexing is a staple in packet switch networks, such as the Internet. Here, data packets, small units of data formatted for transmission, are sent in an interleaved fashion. This means that packets from various data streams are mixed together, traveling along the network side by side, but not necessarily in a fixed order. The flexibility of statistical multiplexing allows for this intermingling, as the system can swiftly adjust to the changing priorities and sizes of the packets. The efficiency of statistical multiplexing is particularly evident in how it handles network congestion. By prioritizing packets based on current network conditions and the importance of the data, it can prevent bottlenecks that might occur if too many data packets demand high bandwidth at the same time. This adaptability not only improves the overall throughput of the network, but also enhances the quality of service for users. Furthermore, the dynamic nature of statistical multiplexing means that it's inherently fair. It allows for temporary bursts in data from any user, adjusting other streams accordingly to accommodate this without significant disruption. Statistical multiplexing adapts in real time, making it a powerhouse in efficient data handling. As we've seen, multiplexing is like a conductor, orchestrating the flow of data streams seamlessly across a single channel. It's the unsung hero of network communications, allowing multiple signals to share a single pathway while maintaining the integrity of each individual transmission. Let's take a moment to recap the different types of multiplexing we've explored. Time division multiplexing, or TDM, splits the channel's bandwidth into distinct time slots. Each data stream is given its own slot, reducing interference and optimizing the use of the channel in environments like circuit switched networks. Then, there's frequency division multiplexing, known as FDM. This method divides the bandwidth into multiple frequency bands, each carrying a different data stream. It's like each stream has its own lane on a multi-lane highway, making FDM ideal for analog systems such as radio and television broadcasting. Moving on to code division multiplexing, or CDM. Here, each data stream is tagged with a unique code. All streams share the same frequency, but are distinguished by these codes at the receiver's end. This technique shines in environments like mobile cellular networks, where simultaneous data transmissions are a norm. Lastly, we discussed statistical multiplexing, which dynamically allocates bandwidth based on the demand from each data stream. This flexibility makes it perfect for packet-switched networks like the Internet, where data traffic is unpredictable and varied. Each of these multiplexing techniques plays a crucial role in enhancing network efficiency and ensuring robust data transmission across various communication environments. Understanding these techniques unlocks the potential for designing more efficient and robust networks. Thanks for tuning in.